Hello and welcome to our weekly roundup of engineering information for the radio and television trade. Today the first of a two-part feature on aerials, starting with the theory of dipoles and leading on to the practical design of a UHF Yagi.
Also today our usual roundup of transmitter news with more Channel 4 installations and details of new television relays at South Brent and Clennon Valley in Devon and Hales Owen in the West Midlands. But first, aerials.
The television aerial is an everyday sight, usually taken for granted it's the key to getting a good picture. For no matter how much you spend on a television receiver, without the right type of aerial, the results can be very disappointing. Aerials appear to come in all shapes and sizes. In the days of 405-line television on VHF, television aerials were quite large, with the rods several feet long, but on UHF the rods are shorter, and usually there are more of them. So just what is it that determines the shape of the aerial?
The job of the aerial is to convert the electromagnetic or radio waves into electrical signals. At the heart of the design of most types of television aerial are two identical metal rods. These are placed end to end with an electrical connection in the middle, and this arrangement is known as a dipole. The length of the rods is crucial, and it picks up most signal when the total length is equal to half a wavelength. So the shorter the dipole, the higher the frequency it responds to. A dipole for the VHF radio band would have a length of about 150 centimetres, but for television on UHF, at the bottom end of band 4 it's down to about 30 centimetres, and at the high frequency end of band 5 it's around just 17 centimetres.
But a dipole to some extent is also directional. It responds best to signals arriving perpendicular to its length, and least to signals coming in from the sides. When the dipole is mounted upright, it responds to vertically polarized radio waves, with little signal picked up from a horizontally polarized transmission. Conversely, if it's mounted parallel to the ground, it responds to horizontally polarized signals, and tends to reject signals that are vertically polarized.
But a dipole on its own will pick up signals coming in from behind it just as well as from in the front. So to reduce pickup of unwanted signals from the rear, a second rod can be placed behind it, slightly longer than the dipole itself. As well as picking up less signal from the rear, we now find that the aerial responds better to signals from the front, by typically around 3 to 4 dB, depending on the spacing. Some aerials have more than a single rod acting as the reflector, and this further reduces unwanted pickup from the rear. By adding more rods in front of the dipole, the gain improves further. This arrangement is named after the Japanese Professor Yagi, who supervised the experiments in the late 1920s of his researcher Yuda. The directors are slightly shorter than the dipole, and the more there are, the higher the gain.
But the law of diminishing returns applies, and after the first few directors, adding more directors gives progressively less and less improvement. Just as important as the sensitivity or gain of the aerial can be the improved directional properties of an aerial which has several elements. This reduces the risk of picking up unwanted signals in the form of either interference or ghosting. But there's more to it than just that. A dipole on its own responds well to only a narrow range of frequencies. By adding a reflector and several directors, and carefully choosing the lengths of the rods and spacings between them, it's possible to broaden the frequency response of an aerial considerably.
But there is a trade-off. An aerial can be designed to cover a small range of frequencies and give a fairly high gain. But for the same number of elements, and with different lengths and spacings to broaden the frequency response, the gain tends to be lower and the aerial less directive. And if an aerial is used to pick up signals outside its designed frequency range, the results can be very poor indeed. The UHF band covers a wide range of frequencies, and it's important to use the appropriate group of aerial for the transmitter being received. An aerial designed for band 4, that's group A, channels 21 to 34, is considerably larger than one for the higher channels in band 5. But you can't necessarily tell the channel group of an aerial just by looking at it. UHF aerials tend to be marked with the channel grouping or colour-coded. Designing an aerial to give an even response over a wide range of channels isn't straightforward. More about the practical problems of making an aerial in next week's broadcast when we visit an aerial factory.
Transmitter news now, and only one item so far of planned work this week. It's at Malvern, where television services are to be off the whole of Thursday morning. This is for aerial work and is weather dependent. Don't forget that up-to-date transmitter news can be found on Oracle, page 697.
New relays now, and near Buckfastleigh the relay for South Brent was tested briefly last week, but was turned off due to some interference problems for people in the Lutton area to the northeast of the relay. We're now hoping to serve Lutton from South Brent